Welcome. We're about to do question 7 of the Electromagnetic Worksheet 6B, Talk on a Coil. So having a look at the question 7, I didn't do 6 because I thought it was a bit straightforward, and if you have any problems, please email me on that one. Question 7 is very similar to our last question, question 5, where we had to do the torque as it went through one revolution, okay? And we noticed that if I mentioned the word commutator, which is in our next section, it's a way of reversing the current in the coil each half turn, but we're not working with that at the moment. So here is a diagram of the coil where it's a absolute value curve, and it just bounces off the x-axis there. So here we've got a very similar graph again. We've got the maximum torque, and then this is a quarter turn, and then here is 1 turn, and so on, okay? And the horizontal axis is measuring time in milliseconds there, okay? But we'll notice something happening to the torque. The torque is reducing. It's going down and then leveling off to a constant value here. And the reason why I wanted to look at this, it introduces a concept called back EMF. Okay. So let's just read the question, and then we'll go through and see what is going on with this back EMF and what is it. A DC motor has a single 5 centimetre square loop, so it's 5 by 5. It's placed in a field of 4.2 Tesla with 2 amps initially flowing through the coil. Okay, so the graph of the torque is shown below, and we've looked at the actual shape of this graph already. Okay, so we've got maximum torque started here. So we're starting at time equaling 0 with a maximum torque. So what would be the initial orientation to get a maximum torque at 0? We would need the coil to be horizontal in the field. Okay, so we know that if alpha is 0 degrees, then theta is 90 degrees, and we get sine of 90, which is a maximum. So calculating that value of M, which is the maximum torque here. So I'll just do it down here. So torque is equal to NBIA sine theta, and it's going to be sine 90 in this case because we know we've just answered the question that it is horizontal in the coil between the two sections of the magnet. We know that N is 1 because it's told that, and B is 4.2, so it's 1 times 4.2 times the current, which is 2, times the 0.05 squared. Working out that current there, we go that maximum torque would be, let's just do it. Sorry, I'm just moving the calculator around so you can see it. 4.2 times, how about turning it on? 4.2 times 2 times 0.05 squared equals, and it's 0.021 Newton meters. So this value up here is 0.021, so 0.021 Newton meters. So what will cause this torque to decrease as time goes on until it gets down to about, according to this, is about half its value? Okay. Well, let's have a look at the formula. What can change in this formula? Well, the torque is changing, but what part of this other part of the formula can change? Well, we know that theta is actually changing, and we are seeing the change with this shape of the graph. So it's not the sine theta that's causing the peaks to drop down. So what else could it be? Well, the area of the coil is definitely not changing. It's a square, it's made of wire, and it's 5 by 5. It can't change. It is between 2 magnets, which is 4.2 Tesla. They're not getting changed at all. And the current is the only thing that can change. It's a single loop, so B is the same, A is the same, so it must be current. So current is reducing. So the reason why we're having the EMF, sorry, not the EMF, the torque on the coil, the maximum torque at the top of each of these crests reducing is the current is reducing. So what is causing this? Well, if we have a loop of wire, so here is our loop of wire, and it is between a north and a south, and we turn it, okay, this will generate EMF. Okay, this is a generator. Okay, but if we wanted to, if we put in a power source, so let's put in a current here through amperage, then this becomes a motor. So a motor is where we put energy in and get a turn, and a generator is where we turn it and get energy out. But notice they're the same structure. A DC or a DC motor is basically a generator. So as this coil does turn as a motor, as the coil turns, it is going to generate some EMF. And that EMF, according to Lenz's law, must oppose the motion of the motor. And therefore, it's going to go and reduce the current coming in. So if there's 2 amps to begin with going through this coil, then as it begins to turn, then the current, there will be a generated current going backward to reduce this 2 amps, according to Lenz's law. And this is called back EMF. Remembering that all motors, all DC motors, act as generators. And as they start and as they speed up, you'll be generating a current that goes against the inward current flow. And that inward current flow, which in this case was 2 amps, will start to reduce. As a result, if the current reduces, the torque on the coil reduces. And this is because all DC motors are themselves act as a generator, and they must produce back EMF according to Lenz's law. The back EMF must oppose the change, and the change in this case is caused by a current coming into the coil causing the turn. So in this case, the back EMF must oppose the turn, therefore it opposes the current's input. Okay, so when it says suggest a reason that the torque on the coil decreases in the first few moments, it's because of back EMF. After a moment, after a while, after about 6 milliseconds, then we stabilize that we will start to get the same back EMF generated for every forward EMF, okay, or forward current, okay. And so what will happen is it will even out with the as time goes on. Okay, we'll definitely be mentioning back EMF a little bit later as well, but because it comes up in this worksheet, we'll start talking about it now.